Let's talk today about nuclear fuel cycle. First of all, please look at this diagram. It's traditional layout of nuclear power plant. And maybe you know that for majority of different nuclear power plants all around the world, first of all, to get some electricity to produce power, we'd like to use turbine. Turbine will rotate turbo generator, and in this way we can get electricity. Only one question is how to rotate this turbine. In majority of types of nuclear power plants, for this reason we can use steam, water steam. And next question, how to get this steam. For thermal power plant, we use different fossil fuels like oil, coal or gas, just to boil water and to get steam in this way. But for nuclear power plant, we'd like to use, for this reason, nuclear energy. So we should to use some nuclear fuel in the core of nuclear reactor, and from this fuel we can get this thermal energy. So in basics of this process, actually, we should to say about nuclear fission reaction. So you see on this slide this idea that for many isotopes, actually not only uranium-235, if some neutron, thermal neutron, will strike with nucleus, with some probability the reason could be splitting of uranium into two byproducts with several new neutrons emitted. And actually in this reaction we can get thermal energy. Actually thermal energy is kinetic energy of neutrons and byproducts flying around of this process. So in general, of course, we can use not only uranium. There are different isotopes of plutonium, thorium, which could be used as well for chain reaction. But in majority of different reactors, actually, we talk about uranium as nuclear fuel. So when we talk about nuclear fuel, we should to say about uranium. And the first question, where we can get this uranium to produce this fuel. So the first stage of nuclear fuel cycle is mining. Because fortunately, uranium is a fossil element. This element could be found on the Earth, in contrast with plutonium, for example. So first task to find some depots or reserve of uranium all around the globe and to mine. Actually, there are three main methods to extract uranium. Actually, two of them are traditional ones, and a third is a little bit new. So, first stage, first method of extracting of uranium from the core, actually it's usual open cut mining. Actually, you see on this slide some example of huge open mining, and in this way, using special trucks, we can get some ore, and uranium will be extracted later from this ore. Of course, this method is cheapest maybe and simplest, because there is no need to construct some deep shafts in the ground. But nowadays it's very hard to find some places on the Earth with uranium suitable to apply this method, because actually many places are extracted yet. So on this slide you see examples of next method. Next method is underground mining. So idea is to extract this ore not from surface but actually from the deep. So in this way we should to go deep into the ground. We should to construct special system of shafts and extract uranium actually in the same way as coal, as many other elements. And this method is time-consuming and expensive, a little bit expensive, of course. And the third method, nowadays, the third method is considered as one of safest for environment and one of maybe most optimal ones. it's actually inside to leaching. You see on this slide some enterprise in Russian Federation for developing of uranium mining in this way. And idea is not to construct very broad network of shafts in the ground. Actually, in place of uranium depots, we should to drill in the ground several deep shafts, and we should to pump in these shafts special chemical solutions. And idea is, in reaction with the solvents, uranium will be really flushed out from the core, from ore, and really there is no need to extract huge amount of ore. Actually, we can extract only dissolved uranium in some solution, and then by filtering, we can get really clear uranium from this ore. And you know, in this way, there is no need really to damage huge territory for extract uranium and so on. And of course, this way is cheapest. So nowadays, this way is very broadly used all around the world. So, unfortunately, from one side I said, great, we can find uranium on the ground and can extract. But from other side, the share of uranium-like element in the ore actually is not so high. Nowadays, really most of mining can get for us actually less than 1% or maybe significantly less of percentage of uranium inside. It means we should to construct special enterprise just to provide extraction of uranium from uranium ore. And then we should to provide refining. Refining or affinage, actually it's chemical process to extract namely uranium, like in clear form. So on this slide you see so-called yellow cake, actually it's product of this process, and this yellow cake actually is some intermediate stage of uranium production. And next, very important and very heavy stage of uranium fuel cycle, it's enrichment. Because on the globe nowadays, there are only 0.7% of uranium-235 or uranium-5 in overall amount of uranium. But unfortunately, from point of view of nuclear physics, especially uranium-235 is most suitable for fission reaction. So, if we just find uranium, extract this ore, then extract uranium from the ore, actually it will be not enough to start nuclear reactor. Especially if you'd like to say about usual water as coolant. So, for physical reasons, we should to increase share of uranium-5 inside of this fuel up to some level. For nowadays, for civil reactors, not for reactors of ships or icebreakers, actually we talk about 5% of uranium-235. As I said, natural level is 0.7%. So actually, this process of increasing of share of uranium-235 from natural one, 0.7% to, for example, 5%, actually this process is called enrichment. This process is very time-consuming and very expensive because there are different methods, physical methods, how to increase this amount. The complexity is because it's not chemical process, because uranium-235 and 230H, basic isotope, actually there are isotopes of the same chemical element, and actually there is no way to use some chemical reaction to increase this amount of uranium-5. So we should to invent new methods. Actually, of course, many methods were proposed many years ago in 60s and 50s. And in Russian Federation, actually, the main method of enrichment, and in the world, one of most promising, maybe, actually, it's enrichment by centrifuge. By centrifuge, on this slide, you see photos from different enterprises of Rosatom State Corporation in Russia. Actually, centrifuge looks like some cylinder. Cylinder, we should to pump into this cylinder uranium in gaseous form as hexafluoride of uranium, and this centrifuge is supposed to rotate with very high rotating speed, And in this rotation, more heavier element, like uranium-8, will be further from the axis. And uranium-235 will be closer to the axis of this cylinder. In this way, really, we can provide separation. Of course, one centrifuge, one element, is not enough to provide high-quality separation. To realize this process, really, we should install really many thousands of these cylinders. So on this photo, you see some scope of this production facility. And on this slide in top right corner, really you see hexafluoride uranium stored in special casks in this enterprise. So after this process, really we get uranium. Moreover, this uranium has been enriched up to required level. So great, it's initial material to fabricate fuel, nuclear fuel. And the basic element of nuclear fuel is fuel pellet, you see on this slide. Very small. Now on this slide and further, all these elements really provided for Russian type of reactors, VVR, reactors on thermal neutrons, which use water as coolant and as moderator as well. So, very small fuel pellets on the next stage should be stacked one by one, and in this way we can form very long cylinder of fuel elements. This cylinder will be enclosed with some special thin tubes called fuel elements. So you see an example of fuel elements on this slide as well. And these fuel elements will be closed from both ends and secured by special welding joints. Because during operation it's supposed that all fuel elements will be hermetically sealed. So, to safely and conveniently operate this fuel on nuclear power plant, for us it's much more preferable to collect different fuel elements in one structure called fuel assembly. In one fuel assembly we have more than 300 fuel elements, fuel rods. Actually, we have special supporting construction and fuel elements. And on this slide you see overall view, and in right bottom corner you see photo of cross-section of fuel assembly. And on this photo you can see fuel pellets, walls and so on, all elements. So the next element, not element but really stage, actually the main one, it's using of nuclear fuel in power production on nuclear power plant. You see all fuel assemblies on nuclear reactor really form special area in the reactor vessel called core or active zone. And especially in this area, fission chain reaction will be initialized and we can get thermal energy, as we said in the start of our lecture. And then we can get heat, which can be used to boil water and to rotate turbine and turbo generator. So, for modern type of fuels, this stage, as usual, lasts around 3-4 years. In average, after this time, fuel will be exhausted, and this fuel should be handled in special way. Because in spite of thermal power engineering for thermal power plants with coal, gas or oil, of course, everyone knows that after operation, coal will be burnt and we will see only ashes. But it's not the case for nuclear power plants, because actually we just load some nuclear fuel inside of nuclear reactor, and after, for example, 4 years, the same fuel will be extracted from the core. Actually, it looks like a miracle, because really, during these 4 years, we got huge amount of energy from this fuel. But actually, in physics, there are no miracles inside, because after operation, really, structure of fuel will be different. Initially, it was only uranium-238 and 235 as main isotope. But after many years, actually it will be the same elements plus some byproducts. Byproducts of fission reaction, actually there are more than 200 different isotopes. Unfortunately, these isotopes, first of all, are reason of rather high radioactivity of spent nuclear fuel, and in this way we should to provide special technical measures to handle with this fuel after operation. First of all, after extraction from reactor, of course, this fuel will be hot, because temperature inside of core are rather high, and especially in fuel there is some thermal production after stop of chain reaction, after shutdown. So, first of all, this fuel should be stored during several years on the nuclear power plant itself, inside of special basins or storage pools, inside of containment of reactor vessel of a nuclear power plant. So, on this slide we see some example with open storage cooling pool with special circulation of cooling water. In this pool, this fuel will be stored during several years. But eventually, in some moment, temperature of fuel will be low enough to provide its transportation. And the next stage, actually, it's first of all transportation itself. As I said, spent nuclear fuel is rather radioactive. So we should to use special containers or casks like depicted on this slide, and in this way we can provide transportation in very safe manner, because that doesn't matter about road accidents, some natural phenomena like, I don't know, storms, hurricanes and so on. Anyway, this fuel will be intact. So in this way we can provide transportation of spent fuel between different enterprises. And final stage for every country really is some disposal, final disposal of spent nuclear fuel. And first of all, we should to provide some steady state for this fuel. Steady means some form just to avoid possible contact with environment and so on. It's one form of this process is vitrification. Really, we'd like to turn our fuel into some form of glass. For this reason, we should to use very high temperature equipment like showed on this slide. And finally, we say about disposal or dry storage. Dry means there is no water, because air is enough to provide cooling of this fuel. So we should use special containers, special buildings on the surface of ground, maybe underground, and of course special systems for monitoring, for protection, for cooling of air in these rooms. But it's not so complicated systems in contrast with wet storage. On this slide, really, you see all stages of nuclear fuel cycle collected all together. From the first one, from mining, and then after all discussed, like refining, enrichment, operation, to keeping of this fuel on the storage pool. But for this picture, there are two ways of closing or termination of this cycle. Because initially, for many years, traditional way, actually so-called open fuel cycle. After operation, fuel should be stored in wet storage, in dry storage, but after decades maybe, finally this fuel should be disposed finally in some special facility. And of course, some big problem how to construct, how to design this facility, just to be sure that this facility will be very safe place for this fuel for many, many hundreds and thousands years. This one way. But for some countries and Russia as well, actually we'd like to promote other way. Other way means closing, maybe partial closing of fuel cycle. It means that after operation in our fuel, as I said, we have uranium first of all, and moreover, amount of this uranium after operation in fuel really higher than initially in the ground. It means it may be economically effective to extract this uranium from spent fuel from one side. From another side, I said for you that we have many isotopes, radioactive isotopes, inside of spent fuel. These isotopes could be considered as very harmful and dangerous from one side, but from other side, many of these isotopes are very, very expensive and very valuable for different areas, maybe for nuclear medicine, maybe for different industrial applications. And if we manage to find some good and economically effective way how to extract these isotopes, it will be great. So, in Russian Federation, there are a lot of different facilities of fuel cycle, so we have some possibilities to realize this way. So, really nowadays in Russia, not all fuel cycle, but some part of these fuel elements really processed in this way. And in this reason, I'd like to say in the end of my presentation about very important direction of future for nuclear power production. It's fast reactors. Fast reactors really, in contrast to usual thermal neutron reactors, really we'd like to use fast reactors with fast neutrons. And one of the main advantages of this kind of reactors, we can use some isotopes which cannot used in usual way for thermal power reactors. So, traditional way, maybe you heard about this, when some specialists said if nuclear power in the world will develop in such way as previously, actually all uranium on the globe will be enough maybe for 100 years. Because, of course, uranium will be exhausted. But if we can realize fast reactor technologies, actually in this way we can extend this time really for 1,000 years. And it will be very promising technology because in this way we can guarantee some source of energy, clean, safe, environmentally friendly way of production of electricity for many, many 100 years ahead. And of course, in this time, we can be sure that other source of electricity, like fusion, for example, will be designed and tested. So, nowadays, Russian Federation is the world leader in technology of fast reactors because we have 2 power reactors on Beloyarsk nuclear power plant. You see one photo of Ben 800 on the Urals mountains. And in the same time, in the Siberia, really some prototype of advanced reactor with lead coolant, so-called BREST, really is under construction on special facility in Siberia. So, actually, we'd like to see in the near future about next success in closing of fuel cycle, and in this way we can transfer nuclear power on the next level of development. So, briefly, I think it's enough about nuclear fuel cycle. Thank you very much for your attention, and goodbye.